There is a newer version on Blackboard of this lecture. It should have a 2022 date on it. Please download that to get the most up-to-date one. I'll just give you a couple of minutes to download it. The lab exam you should get tomorrow. That's very likely tomorrow. And what did Dr. Humboldt send anything for the written one? Okay. That shouldn't take. I mean that you should get tomorrow also. The lab exam takes longer to grade because we've got to go through all the questions. Like there's a lot more variety of responses there. So you have to be careful grading that in a different way to like the multiple choice. The multiple choice is like pretty much automatic, but it doesn't work for the lab exam. Okay, so we're talking about blood and hematopoiesis. Like one of the reasons I put this newer version up is like there's different ways that you can sort of talk about this. You can sort of start with hematopoiesis and sort of explain where the blood cells come from, or do it the blood first and describe the different cells, and then explain how they're created. And there's pros and cons for both, but I found that like doing hematopoiesis first is a little confusing because you don't really know what cells I'm talking about. So it's sort of, although you can do it both ways, it makes more sense to do the cells first. Before we do that, like let's just look at blood in general, like in terms of its functions. It's got several important functions. First of all, transport. So as you know, it's carrying oxygen and CO2. It's also carrying nutrients and waste products, regulatory molecules such as hormones. It's involved in homeostasis, thermoregulation. And it's also have quite an important protective function in terms of vascular integrity, coagulation, blood clotting. And then the immune cells are being transported in the blood as well as antibodies. The typical human blood volume is 7 to 8% of the body weight. And it's also important to realize that the O2 and CO2 are transported via different mechanisms, and I'll go into that later as we go forward. So what about some of the clinical aspects of it as well? So the first few slides are just like an introduction. You can separate blood out into different components, and typically you're going to centrifuge it. So you would be centrifuging and separating it out into three major layers. The upper layer is known as plasma, and that's about 55% of the blood volume. And that's the least dense component, that's why it's going to be at the top of the tube. The buffy coat is the middle, which is only about 1% or less of the blood. And that's basically where you find the leukocytes and platelets, the white blood cells and platelets. And then the densest component are the erythrocytes, which can vary quite a bit actually in terms of percentage, but like an average would be around 45. And that's the most dense. We'll talk about that variation in a little bit. And the buffy coat and the erythrocytes are known. Let me get this. The buffy coat and the erythrocytes are known as the formed elements. So termed because they are formed in the bone marrow, basically. So, whereas the plasma, you can have those components coming from elsewhere. But basically, the buffy coat, the leukocytes, platelets, and erythrocytes are made in the bone marrow, known as formed elements. It's also worth keeping in mind, as we talked about earlier on, that blood is classified as a special, a special type of connective tissue. And as I said, you can separate it out. And typically, you're going to be adding an anticoagulant before you do the centrifugation. So that's like almost, most of the time, like an anticoagulant will be added. And you basically end up with, as I said, plasma. So this is pretty similar to the previous slide, but just a bit more detail in terms of listing like the components of the plasma. So you're going to have like albumin, fibrinogen, which is a clotting protein, immunoglobulins, lipids, lipoproteins, hormones, vitamins, salts, etc. So all the sort of soluble components are going to be in the plasma. And then again, the buffy coats and the platelets in the middle, about 1%. And then that red blood cell layer, the erythrocyte layers, also known as the hematocrit. You might have heard that term before. And as I said, that can vary, and it's clinically relevant as well, this percentage, that again, I will come back to. There's another way to centrifuge blood without anticoagulant, and that will cause it to clot. And you basically have a similar thing happening, like with the red blood cells, white blood cells down here. But you don't get the 3 layers, it's typically 2 layers. And the upper layer is known as serum, which is similar to the plasma, but basically you have the clotting components like fibrinogen sort of adhering to the red blood cells, platelets, and so on, and forming this blood clot. So serum is very similar to plasma, but it doesn't have the clotting proteins, like they will spin out because with the plasma, you're adding an anticoagulant. With this, there is no anticoagulant. And you sometimes hear these terms like serum and plasma used interchangeably, but if you want to be like really correct, they're different things. So the serum is without the anticoagulant, and the plasma is with the anticoagulant. And a normal blood volume would be about 5 to 6 liters. So let's go through now in more detail and look at some of these components. So as we're going to look at the plasma and formed elements in turn. So the plasma is basically the liquid portion, mostly water, with various dissolved substances, electrolytes, gases, nutrients, and so on. And then you have various proteins in there as well. The most abundant being albumin. That's about 65%. And that's responsible for the blood osmolarity and viscosity. But there's also other significant proteins as well. So the fibrinogen that I mentioned is involved in clotting. But you also have globulins, such as antibodies, as well as storage and transport proteins. And some of these will be coming from various locations, such as, for example, the thyroid globulin. So basically, various organs can make proteins that are secreted into the blood. And quite often hormones are not just free floating in the blood, like they're bound to globulins or transport proteins, typically. And then antibodies are also found in the plasma. And this is just a bit more detail about the components of the plasma. It's about 90% water, 7% proteins. And then you have ions like bicarbonate, potassium, sodium, small molecules like glucose, lactate, and then lipids, free fatty acids, triglycerides, and cholesterol. So that's basically the plasma. Let's look at the formed elements, the blood cells. And these are basically split into three major components. The erythrocytes, the red blood cells, carrying hemoglobin, and they are about 5 to 6 by 10 to the 6 per cubic millimeter, like the density in the blood. And you want to make a note of these values. Leukocytes, sometimes spelled leuko, the K, is the white blood cells. And they're basically the major component of the immune system. And they are 5 to 10 by 10 to the 3 per cubic millimeter. So about 1,000-fold less than the erythrocytes. And then the thrombocytes, the platelets, which are involved in blood clotting, a major initiator of blood clotting, are about 150 to 200 by 10 to the 3. A typical ratio for these is actually given as 600. So there's typically 600 as many erythrocytes as leukocytes, because you have that variability here. Like you'll see like an average. So even though I said 1,000, like the average kind of ratio that you see sort of listed is 600, and you want to make a note of that also. So 600 as many erythrocytes as leukocytes, typically, the ratio. And these are those formed elements, like in a visual form. So you have the red blood cells, the platelets, and then the white blood cells, the leukocytes. And there's basically only 5 white blood cells. So, we'll go through these and describe their characteristics. But it's worth keeping in mind there's only 5. Like there's 5, you can divide them up further, but like there's basically 5 major types. And those are the monocyte, the lymphocytes, the eosinophil, the basophil, and the neutrophil. And then the other 2 things are the red blood cells and the platelets. So all together, you're basically dealing with 7 major formed elements. And this is just a bit more detail of the values that you see for those. So starting with the erythrocytes, in a male, typically 40 to 50% of the volume of the blood, and then 4.3 to 5.7 million per microliter. In females, the value is typically around 35 to 45, and 3.9 to 5 million per microliter. Leukocytes about 1% of the total volume, and platelets 1% or less of the total volume. And basically that hematocrit is referring to the percentage, as I mentioned. It's basically the same, it means the same as the percentage of the volume. And it's determined by the centrifugation that I mentioned. And that hematocrit can vary, as I mentioned. Like if it gets too high, it can predispose to blood clots, strokes, heart attacks, and so on. So if it gets above 50, then it becomes like a clinical concern. If it gets below 35, then you're getting into the territory of anemias, like low red blood cell counts, and so on. So, like 35 to 50 is considered. Well, in females, it wouldn't be anemia at 35, but like say less than 30. For males, about 35. You're basically got the two extremes on either side: excessive blood clotting or not enough blood clotting. Heart attack, strokes, anemia. The leukocytes, the white blood cells, as I mentioned, there's 5: the neutrophils, the eosinophils, basophils, lymphocytes, and monocytes. Red blood cells are about 99% of the blood by number. In terms of lifespan of the cells, the neutrophils are only about 12 to 14 hours, although that can be extended if they're activated through infection and so on. Platelets are about 10 days. Red blood cells, 4 months. And lymphocytes can be many years. So, especially if they're so-called memory cells, like they go into, after an infection, some of them can migrate back to the bone marrow and take residence there, and they can provide long-term immunity. Often for, even can be a lifetime. So let's go through the cells now in more detail, the formed elements, starting with the red blood cells. When you do, you'll see all this in the lab as well. Basically, you can spread spread the blood cells on a slide, just like similar to a typical histology slide. It's known as a blood smear, and you can similarly stain them with H&E. And you're going to see like most of the cells will be red blood cells. So it just follows the pattern that you would see in the blood. And you may occasionally see some cells with a bit of material inside. Those are known as reticulocytes, which are the last stage of the maturation of the red blood cells from the precursors. So what a reticulocyte is it may contain some remaining organelles, like rough ER or mitochondria, something like that. So they're only about 1% of all the red blood cells, but they are, you'll see some. And the basic shape of the red blood cell is kind of like a donut, but it doesn't have a complete hole in the middle. It's got like a large indentation, but it's still solid in the middle. And the size is about 2.6 I'm talking about sort of the depth of the cells, about 2.6 at the rim, at the edge, and 0.8 micrometers in the central area. And that's how it looks on a diagrammatic form. Basically, like I said, like a donut, but not with a complete hole in the middle. And as you know, the actual diameter is about 5 to 7 or so across the cell. There is an important protein that's found in the membrane of the red blood cells that is kind of unique. You don't see it elsewhere in most other cells. It's known as spectrin, and you want to memorize that. It's basically sort of resembles a cytoskeletal protein, but it's actually in the membrane itself. So it kind of resembles actin or the microtubules, but it's actually in the membrane. This sort of teal colored fiber is the spectrum, and it binds to various other proteins to further, its basic function is to stabilize the membrane of the red blood cell and also give it some flexibility. So it allows it to be flexible, but it also maintains the shape. So it has some properties that are kind of unique. And it binds to some cell surface proteins and some cytoplasmic proteins. And even actually binds up with actin in the cytoplasm. So you want to memorize that spectrum molecule as being like essential for the membrane and flexibility of the red blood cell. Also, another aspect of the erythrocytes, red blood cells, I've talked about but didn't really go into detail yet, is the transport of the gases. So basically, the oxygen is carried. So this figure is basically showing the lungs over here on the left, and then the tissues on the right. And this represents the plasma, this represents a red blood cell. So you have oxygen coming in from the air. It binds to, in the lungs, it binds to hemoglobin. It's transported on the red blood cell and then is released in the tissues from the hemoglobin. For the carbon dioxide, it's actually converted into a bicarbonate ion. And not all of it is actually transported on the red blood cells. It can be transported through other means, or it's not necessarily bound to hemoglobin, let me put it that way. And you don't, I won't go into the details, but the main thing to remember is it's converted into bicarbonate by this enzyme called carbonic anhydrase that basically takes carbon dioxide and water and combines them into a bicarbonate ion. And then it reverses basically the mechanism and releases CO2 back into the lungs once the cells reach the lungs. So it's incorrect to say that the carbonic anhydrase is carrying the CO2. It's just basically converting it into the bicarbonate, and then can be bound to hemoglobin, it can be bound to other molecules, and it's basically that bicarbonate is transported back to the lungs. So that's sort of the basics of the gas transport. And then the quality control is also important, like when the red blood cells age, they can be phagocytosed by macrophages in the liver and spleen. So when they reach that 120-day limit, they're basically broken down, molecularly recycled in the liver and spleen. There are also some clinical disorders of the erythrocytes. 4 major ones I've listed here. The most well known is sickle cell anemia, which is a mutation in alpha-2 beta S2 of the hemoglobin. And it basically changes the shape of the red blood cell into a less flexible, deformable, sickle-shaped cell. So what that means in terms of the blood vessels is like the sickle cell tends to clot slightly more than the oval-shaped red blood cell. And particularly in states of stress, so if adrenaline is released, norepinephrine, epinephrine, and so on, it can precipitate a so-called sickle cell crisis because the clotting is increased under the stressful conditions. So it basically is, sickle cell, you could say, is essentially a coagulation disorder as a result of the the shape of the cells. It also confers malaria resistance. So, and quite dramatically, basically the malaria bacterium cannot infect the sickle cell shaped red blood cells so as easily as the oval shape. So that's basically the origin of the malaria resistance. And even in a heterozygous state, it can confer some malaria resistance. The next one is elliptocytosis, where you basically have oval-shaped red blood cells. So they're kind of more flattened, if you will. That's caused by a mutation in that protein I just mentioned, spectrum. Or some of the binding proteins to spectrum can be involved. But it basically affects the ability of the spectrum to maintain the shape of the membrane. That's known as elliptocytosis. The next one is thalassemia. You have defective synthesis of the alpha or beta chains of the hemoglobin tetramer. And that's basically leads to an anemia. So there's insufficient synthesis of the hemoglobin. So there's insufficient oxygen transport, essentially. And then the fourth one is macrocytic anemia, where you have larger than normal red blood cells, whereas microcytic is smaller than normal red blood cells. The macrocytic is more sort of concerned with vitamin deficiencies and so on. So if you have, in particular, a vitamin B12 deficiency, can cause something called pernicious anemia that you might have heard of before, which is basically causes the red blood cells to enlarge as a sort of compensation for the lack of vitamin B12. And all of these you can look into in more detail if you have time. And then lastly, I mentioned the reticulocytes. This is just a slide sort of giving a bit more detail on that. They're the last stage of the red blood cell maturation. Only about 1% will be seen in the blood. This is a comparison between like a red blood cell here and a reticulocyte. You'll see fragments of various organelles basically in the cytoplasm. Seeing the same thing here. And under an EM, you can actually sometimes see mitochondria, bits of Golgi, etc. So that's the essentials of the red blood cells. Let's move on to the leukocytes. And these are split into two major types, the so-called granulocytes and the agranulocytes. The reason the cells are called granulocytes is because they literally contain lots of granules in the cytoplasm that contain different enzymes for each of the three. And then the agranulocytes, of which there are two types, they don't have these specific granules. But there's some important details to that. The main one being that all of the leukocytes do actually contain primary granules. So these are basically lysosomes. They may also contain microbicidal agents, such as myeloperoxidase. So all of the cells contain those primary granules. But there's so-called secondary granules that secrete various inflammatory mediators that are unique to these three cells. And it's really the secondary granules that give them the granulocyte morphology or behavior. So it's not the primary granules, it's the secondary granules that basically create the granulocyte. So in other words, even a lymphocyte and a monocyte will contain the lysosomes, which are the primary granules. So they all contain these azurophilic primary granules. And I'll talk about the granules in more detail. Also, they're typically larger than red blood cells, twice or even 3 times the diameter of a typical red blood cell, and that goes for all of the leukocytes. And you can basically measure the concentration with a blood smear. So you, just like you saw with the red blood cells, you can, about 1% of those cells on the smear will be leukocytes. And you can basically count those, and they have quite different percentage concentrations, even within that 1% of the total cells. There's a lot of variability in the concentration of the individual leukocytes. So the typical value for a neutrophil, for example, will be around 60%. And that's by far the most commonly seen white blood cell in the blood smear. And these upper 3 are the granulocytes. And then next you have the eosinophil at about 4%, and then the basophil at about 1%. It can be even lower, like 0.5%. And then the 2A granulocytes, the lymphocytes, will be about 26%. And then the monocyte at 9%. And you could even rearrange this table if you want, just in terms of percentage. So you could go neutrophil, lymphocyte, monocyte, eosinophil, basophil. This is divided up into granulocytes and agranulocytes. And they basically stain differently with H&E, or there's a similar dye called Wright stain, and with a spell with a W, Wright. And they basically have different staining properties on the slide. And that gives rise to their names, actually. So, a neutrophil doesn't really stain, excuse me, doesn't really stain strongly with either H or E. So in the cytoplasm, you kind of have a sort of lightly pink appearance. So it's neutral stain, hence neutrophil. The eosinophil stains strongly with eosin, the granules. So these would be the secondary granules that are being stained, and they stain with eosin, and hence eosinophil. The basophil stains with basically you basically have the it basically likes basic dyes, hence basophil, and you basically have the granules staining dark blue to purple stain in the cytoplasm. So it's quite a different. So basophil is literally means likes basic dye. Eosinophil is basically likes the eosin. So that's the origin of those terms. And the neutrophil doesn't stain much with either. So you kind of have this paler cytoplasm. And then the 2 agranulocytes on the right, they're not going to be staining the secondary granules. And the way to tell them apart is the monocyte is pretty large and will have a bean-shaped or a kidney-shaped nucleus. So that's like a very easy way to recognize it. Whereas the lymphocyte will have a round nucleus that takes up almost 90% or more of the whole cell. So there'll be very little cytoplasm in the lymphocyte. Okay, so that's like the 5 basic leukocytes. So let's go through them in turn, starting with the granulocytes. they typically have like a multi-lobe nucleus. So the most extreme is the neutrophil, where the nucleus can almost appear to be broken up. But it's not actually broken. It's joined by thin bridges of chromatin, but it can look very disjointed. But you see even an irregular nucleus, even in the eosinophil and the basophil. So they all have that. And that can help to identify them, but the easiest way is basically looking for what the specific or secondary granules are. And this is just a diagram of the three: neutrophil, eosinophil, basophil. And they all can have like a phagocytic property as well. So they can be classified as phagocytes also. So let's go through the three. Starting with the neutrophil, as I said, they're 60 or even higher, 65% of the normal white blood cell count. They're the most important phagocytic cell. They're also sometimes referred to as polymorphic nuclear neutrophils, just because of that irregular shape of the nucleus. Spend about 8 to 10 days in circulation. That would be in an activated state, where they engulf bacteria, viruses, infected cells, debris, and so on. And as I said, there's two types of granules. The specific, or the secondary, which are the most numerous, and they contain bactericidal agents, including lysozyme. And it's the primary granules that are actually lysosomes, and they contain peroxidase and other enzymes. And basically, the specific or secondary granules do not stain strongly with either the H or E. And that's like a large magnification. You can actually see here some granules, which would be a mixture of primary and secondary. And they can actually move out of the bloodstream. So that's an important aspect of the neutrophil. Just like you've seen, macrophages can be in connective tissue, like we talked about that earlier. Neutrophils can also exit out of the blood vessels into the connective tissue. And this is known as diapedesis. This phenomenon is known as diapedesis. And basically they bind to a protein on the inner cell wall of the endothelial cells called selectin. Excuse me, take that back. The selectin is on the cells. The selectin receptor is on the endothelial cells. So you have a binding of the selectin protein to the selectin receptor. And it basically allows a tight adhesion of the neutrophil to the endothelial cells. It's also strengthened by integrin, with integrin receptors. So that is how they bind to the blood vessel wall on the inside. And you then also have signals from the outside of the vessel, which can be through, say, a mast cell, like we talked about that earlier as well, of how a mast cell can release heparin and histamines and proteases that basically break or weaken the bonds, the intercellular bonds between the endothelial cells. And that allows the neutrophils to exit through the gaps between the endothelial cells. And they will literally go out into other tissues and secrete chemoattractant molecules to bring in other cells and so on. And neutrophils are basically the principal defense against acute bacterial infection. That's why they're so numerous. Like they are like the first sort of line of defense against pathogens. And they are phagocytic just in the way that a macrophage is. So they will recognize opsonized bacteria, which we talked about before as well, and basically bring them into a phagosome and digest them in lysosomes. And also the specific granules play a role there as well. So you can basically see ingested bacteria being phagocytosed by the neutrophil. So that activity is similar to a macrophage. Okay, so that's the neutrophil. The eosinophil is the next granulocyte, about 12 to 7 micrometers in diameter. They have that same bilobe nucleus, and they're larger than a neutrophil, and they're easily recognized by that bright red staining of the eosin granules. They will be around 2 to 5%, 4% on average of the circulating leukocytes. They too can enter the connective tissue from the blood vessels. And they also participate in triggering asthma and are involved in allergic responses. One thing that they do is, an important thing that they do, is that they can also dampen down the allergic response by counteracting the action of the basophils and the mast cells by secreting an antihistamine or histaminase or other enzymes which basically combat the inflammation induced by mast cells and basophils. So you can kind of think of it like a yin-yang type thing, where the eosinophils are sort of decreasing that release of histamine and various other molecules by secreting enzymes that break them down. So that's an important function of the eosinophil, this antihistamine activity. And that histamine is being released by mast cells and basophils, which we haven't yet got to. And that's how they look. They basically have hundreds of these eosinophilic granules in the cytoplasm. And the main protein in those granules, it's called a crystalloid body, which contains 4 major proteins. The most important one being major basic protein. So you want to memorize that, or MVP. It's localized in the crystalloid body, which are these sort of crystals in the granules. And that's sort of what's accounting for the major intense acidophilia of the granule. But you have those other 3 as well, the eosinophilic cationic protein, eosinophil peroxidase, and eosinophil-derived neurotoxin. But the most important is major basic protein, MVP. You want to memorize that, MVP, which is sort of the most significant factor in the crystalloid body, forming granules. There's also other molecules there: histaminase, arosulfidase, collagenase, spelled wrong, and cathepsins. Plus, they also have the primary granules, sometimes called azerophilic granules. And as I said, all the leukocytes have those. And basically, the eosinophils are involved in allergic reactions, parasite infection, and chronic inflammation. Interestingly, you see them a lot in the intestinal wall, even more than the bloodstream itself. So that's another, like a unique property of the eosinophils, is that they tend to migrate into the intestinal wall, particularly during an infection with an intestinal parasite. And that would be something like a tapeworm or something like that. You basically see in an infection, if you take, say, a slide of the jejunum, you would actually see eosinophils in the connective tissue that you wouldn't normally see. You can also see increased levels of eosinophils in the blood if someone is in a state of allergy or asthma. So they increase to a higher percentage. That's known as eosinophilia, like increased eosinophils in the circulation. And that's basically seen in an intestinal parasite infection, or you can also see it in asthma or an allergy. With the intestinal parasite infection, it would be, you would also have it being seen in the intestine as well, whereas it's not, it's more in the blood in the case of asthma or allergy.
I got
So,
a question.
yeah.
Since they're staining pink, does that mean that the granules are basic? Because the neutrophils and the basophils are purple. So I was like, is that why it's obviously what they do?
The granules are actually acidic. Yeah. So, yeah.
I thought it was pink that was basic.
Sorry?
I thought it was pink that it was basic.
Wait a minute. It's been a little bit. For some reason, I'm like,
It was just a random question.
no, it's a good, so H and E, so the hematoxylin is, yeah, excuse me. So it's H and E, right? Hematoxylin, eosin. The hematoxylin is going to be staining usually DNA, which is God, what's wrong with me? The hematoxylin is staining the DNA, which is acidic, and stains it blue. Okay. The eosin is staining the proteins, which are basic, and it stains them pink. Yes, you're correct. So the actual material is basic, and it's binding to an acidic dye.
I got you.
Yeah, so you're right. And yeah, I mean, the easiest way to remember it is like H and E is like, it basically follows the order of transcription, DNA to protein. So H and E, DNA to protein. The hematoxylin is binding to the DNA, which is acidic and stains it blue. The eosin is binding to the protein, which is basic and stains it pink.
Gotcha.
And that is pink, therefore it is basic.
Thank you.
You're welcome. Okay, so, and that is in fact makes sense because you got the major basic protein there in the granules. So that's absolutely correct. So, yeah, eosinophilia is an increased amount which can be caused by either of these two conditions. So that's basically it for the eosinophils. Let's go to the basophils. They're 14 to 16 micrometers in size, bilobed, just like the other granulocytes. They have basophilic granules in this case. They're larger than the eosinophils and neutrophils, but they're also the most rare. So they're 1% or less. Sometimes you may not even see them on a slide. So I've seen slides before where you can't find them. So there's probably, you basically see them more during infections where they're releasing histamine and heparin. Also molecules called leukotrienes. They're similar to a mast cell in that they release the histamine, which can make blood vessels more permeable. And they also secrete heparin, which inhibits blood clotting. So they're functionally pretty similar to mast cells. But a mast cell is typically seen in the connective tissue, whereas the basophil is in the blood itself. And it used to be thought that mast cells were derived from basophils, but that turned out to be incorrect. They are actually have a different origin in the bone marrow, but they have a very similar function. The cytoplasmic granules in the basophils contain proteoglycans, which you've seen in other cells that give them this property of like an intense metachromatic staining. And those proteoglycans are a mixture of heparin and chondroitin sulfate. And that's how it looks, basically, these basophilic granules. They can almost kind of obscure the nucleus itself. You can sort of see the cytoplasm here is different. If you look closely, it's different to the actual nucleus. And they also have a modulatory function on other cells. They can modulate the immune response of other cells, and are again involved in a defense against intestinal parasites. So this is again just one basophil full of granules, which are also visible on EM extensively through the cytoplasm. And their major sort of role, if you will, is during asthma and allergy. So that's what they're most known for. They will infiltrate the bronchioles during an asthmatic attack, nasal passages in hay fever, inflammation and other allergies. And they release these molecules, histamine, which we've talked about quite a lot already, and also interleukins, which are sort of pro-inflammatory molecules that sort of bring in other cells and molecules. So the basophil, through the histamine and interleukin, is sort of responsible for what you see in situations like hives, hay fever, anaphylactic shock. As I said, they're closely related to mast cells, but they're in the blood, whereas the mast cell is in the connective tissue. And that's just showing those two major molecules being released, the histamine increasing vascular permeability, which can also cause smooth muscle contraction. And in the interleukins, which can promote differentiation of lymphocytes, and so on. The basophils have IgE receptors on their surface. If they become cross-linked, they will release large amounts of inflammatory mediators which can actually damage normal tissues. So in extreme cases, if that sort of process is too strong, it can actually harm the body's own tissues. So it's good to like make a table of these three, which is shown here. So you want to know the basic kind of appearance, which I've described, and there's a table here basically summarizing the properties of the neutrophil, eosinophil, and basophil as a comparison. You don't need to memorize like word for word, but it just sort of summarizes the properties of the three. And you know, you don't want to. I advise not to like overthink these three either. In other words, the neutrophil, eosinophil, and the basophil. Like if you look too much into it, you can kind of go down a rabbit hole because you know, there's a lot of stuff online in textbooks about histamine being released and proteases and so on, and it's sort of like a bit vague, if I'm honest. So you want to try to keep these three as clearly as you can in your mind, without going too much into the details. So I recommend like not to. If you look these up in a textbook, like don't sort of get too into it. It's not profitable. Expense of your time. Okay. The main thing is to recognize them and be aware of the major features. Okay. So that's it for the granulocytes. We now get to the agranulocytes, which are the other two out of the 5 white blood cells. Let's look at lymphocytes first. These can be small or large. This is a large lymphocyte, about 50% bigger than a small lymphocyte. But in either case, the nucleus takes up around 90% or more of the cell volume. This is like an easy way to recognize them on a blood smear. The whole cell will be mostly nucleus. And they're divided up into 3 basic types of cell. The T cells, which can be further divided up into different types. What's going on? What?